Now, till yesterday, we had taken overview of centrifugation process, the principle of centrifugation, right? And what are the different types of rotors. Overview of that we had taken in the previous lecture. So, what is the formula or equation to describe the centrifugation principle? Then, how you can correlate it with revolutions per minute and relative centrifugal field, RPM and RCF, how they can be calculated, what are the factors which contribute to the sedimentation of a particle, including the characteristic of the particle, the characteristic of the instrument, as well as the suspending medium in which the particle is present. So all these things we had talked in previous lecture. All right. So now let's go into the details of each of these. Now, when it comes to centrifuge, the rotor is the main component we have seen, because the type of rotor is going to have effect on the sedimentation and the application of centrifugation process. So you have to choose uh, appropriate design of a rotor so that the desired centrifugation process can be efficiently completed. So why and how I'm saying this, how it would be working, that we have to discuss. So when it comes to fixed angle centrifuges, then you have swinging bucket centrifuge, continuous flow centrifuge. So this is based on the design of the rotor that you classify the centrifuges. Based on the applications, you classify the centrifuge as clinical centrifuge, laboratory centrifuge, and those for industrial purpose, industrial centrifuges, which are mostly continuous flow. From rotational speed, that is what you have learned earlier, we call it as low speed centrifuge, high speed centrifuge, and ultra high speed centrifuge. All right. And fourth category, based on which you can categorize centrifugation type, is density centrifugation, density gradient centrifugation, differential centrifugation, isopycnic centrifugation. And last would be the size and capacity of the instrument. So when it is overview of types of centrifuges, this is how we classify based on the design, based on application, based on rotational speed, preparation, sample preparation principle, sample separation principle, and size and capacity. So we have to look into details of each one of these part by part. All right. Now here I go to the first slide where we are talking about fixed angle rotors. So as we have seen in the previous discussion in the overview, the rotors are of a specific design with a fixed angle. So this angle we are going to measure, we measure it with reference to the uh, central shaft of the instrument. What is the central shaft that we have discussed yesterday? That is the shaft on which the rotor is mounted, right? So that is the central axis of the entire system, and the balance of the rotor also is based on the shaft. So it is the central axis, and with reference to the central axis, you are having a rotor where the position of the tube is arranged such that the tubes are held at a fixed angle. So generally it is 14 degree to 45 degree angle that is there. So this is useful for separating simple mixtures, for pelleting of bacteria and cells, etc. The denser particles in the solution separate towards the angle of the centripetal force. What is the angle of the centripetal force? Centripetal force is towards the center and centrifugal is away from the center. Right. So when you talk about fixed angle rotors, the second row here, you see the horizontal position of the tube, which is with reference to the central shaft. Now, as the particles, they will migrate. We think that when centrifugal force is applied, the particle migrates toward the outer wall and then settles at the base, right? But here you can see the pattern of uh, sedimentation and ultimate sedimentation that happens when you are going to use fixed angle rotor. So the settling particle migrates towards the angle of centripetal force. See this angle, right? And you get a pellet at the base in this corner, and at the end of the centrifugation, the tubes are, when you are removing the tubes, they are at the the sedimented particles are at the base. So that is what you call it as pellet. When it is about swinging bucket rotor, as you see in the in the first position of the diagram, the swinging bucket rotor, as you start the rotor, as it accelerates, the tube gets flanked out and it gets arranged perpendicular to the central shaft. Right, so it is used for heavier and more viscous materials. Tubes are vertically while at rest, and they are horizontal when the acceleration is on. And it is useful for pelleting as well as for rate zonal density gradient centrifugation processes. Now, what is the use? The last point, if you see, it says it minimizes sedimentation on tube walls. So, adherence of the settling particles on the tube walls, it is minimized when you are having swinging bucket rotor type. When it is vertical rotor, tubes are in a vertical position, as you see in the third row of the diagram. They are parallel to the central shaft, and it is used for isopycnic separation and gradient density cushion separations. We will talk about each of these types in the next lectures. So each type of arrangement of tube with respect to this the type of centrifuge rotors is applicable or is useful for specific purpose, right? So for simple pelleting and separation of bacteria and cells, you use fixed angle rotors. Here, swinging bucket rotors are used for rate zonal density gradients as well as for pelleting. Vertical rotors are mainly useful for isopycnic separations. So uh, based on the application, you have to choose the type of rotor. So choice of rotor is going to depend on what is the purpose of your experiment, uh, what kind of separation you are attempting, then desired volume and desired g force. We have calculated the value for g, 10,000 rpm, that is how you talk, and 10,000 g, it is something different, right? Gravitational force that is acting also is taken into consideration when you are saying g force. Right, so this is the overview of these different types of rotors. Now, before I go to the calculations, I have to talk about each one of these rotors to little details. So for example, when I say, yes, fixed angle rotor. Now, when I say fixed angle rotors, the tubes are located in the holes and the rotor body. So this is the diagram that shows the design of it, right? This is the common rotor that we have in our laboratory, you might have observed. So this is the rotor, and these sockets, they indicate the position of the tubes or the tube holders, right? So the tubes are located in these holes or tube holders, and the body is set at a fixed angle, right? The tube is at this particular angle, so 40 to 45 degree maximum, as compared to the vertical position or the shaft. You can measure the angle, and it is about 14 to 45 degrees. So when the centrifugal field is applied, and this centrifugal field is going to be exerted at an angle to the tube wall, right? So if you imagine a tube which is rotating in this kind of a rotor, right? I shall get to the slide which shows a tube which is held at fixed angle, right? So when this is what we are talking about. So when the centrifugal field is applied, and it is exerted at an angle to the tube wall. So the the centrifugal force which is going to be working, it is going to be exerted at an angle to the tube wall, and particles will move outwards. Like here you see some particles are here as settling, they are away from the center, they are away from the solution, they are going to the outer wall. So they are going to move to outer wall, and they will move a short distance before they reach to the outer wall and collide with the outer wall, and they will then precipitate, right? So a region of high concentration is going to get formed, right? So because particles are moving out, they are sliding down a short distance and they are precipitating. So you can imagine what is happening is that the concentration is going to get build up at particular regions, right? So density is greater in that region as compared to surrounding medium. You can see here if the particles are distributed all over, so density of this zone, and if the particles are getting settled at the wall, so density of particles at this zone is much more. So this is going to be more denser than rest of the volume. So sedimentation would occur, and it will form a compact pellet, right? So when you are talking about the path, that is the distance the particle has to travel, so a short path of the tube wall, and uh, when I say short path, that is if it is very close to wall, it has to travel very less distance. So short path is it has to travel before it settles, right? That is one point. And second is, one factor I had talked about in the yesterday's lecture, that is wall effect and convection currents. So outward you are forcing the particle, but at the same time there are certain opposite forces which are working. Positive forces is centrifugal field and gravitational field, which is going to facilitate sedimentation. However, however, when I talk about convection currents, so they are going to push the particle back to the center of the tube. So they are oppositely working forces, right? So if the path length, the distance to be traveled is less, convection currents which are going to get generated also will be less. So, but convection currents would be less at the denser layer, right? So rapid collection of the particles will happen here and they will settle out fast. So when the particle is running from the uniformly distributed condition to the next step, that is they are getting arranged on the outer wall and they start settling. If you remember this sequence, then the strong convective flow is going to get produced uh, during separation, which is going to be a unwanted effect, a undesirable effect, right? Because it is oppositely working. So it is going to interfere with sedimentation. So when it is about the fixed angle rotors, it is important for differential separation of particles whose separation is what? When you are going to separate different particles, say components of a cell. So different components are getting sedimented at different rates. So the point is sedimentation rates they differ, right? And that is where the fixed angle rotors are of importance, right? So uh, here the rotor or the pocket in which you are keeping that centrifugation tube is at a fixed angle, right? So the solution in the centrifuge tube is going to reorient itself. If you remember this diagram, the way it gets reoriented, the solution gets reoriented when it is accelerated. So reorienting uh, during acceleration and reorienting back to the original position when you are going to stop the rotor, when the centrifugation gets closed, right? So this reorientation of solution is is different for each type of rotor. So if you see this reorientation for fixed angle rotor, this is for swinging bucket rotor, and this is for a vertical rotor. So orientation of particles which are sedimenting, these dark colored lines, they show how the particles get reoriented. So very well it is seen that they are different in each type of rotor system. So uh, 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 for isopycnic centrifugation, reorientation of the solution in the tube is going to be important, is going to be advantageous, because it is going to enhance the loading capacity of the gradient, and it will increase the resolution of sample. So fixed angle rotors, when we talk, yes, they are of use for pelleting. They are also useful when we talk about differential centrifugation, right? Now when I talk about vertical rotors, right, this particular condition, uh, third one, and to go about the details on vertical rotors, let's see the next slide. So here it is about fixed angle rotors, right? So fixed angle rotors are we have talked about just now. One more concept here is K factor, and this K factor is going to talk about efficiency. Now K factor, what is K factor, how it is calculated, what is its effect, we will see in the next slides. But now let's talk about vertical rotors. And so when I say vertical rotors, they are highly specialized, right? They are typically used to band DNA in cesium chloride. So vertical rotors have very low K factor, which is useful if the particle must only move a short distance until it pellets. Right? So this is a simple and small description about the vertical rotor. But again, going back to the previous slide, you can get more information on the vertical rotors, which talks about uh, uh, sedimentation equilibrium is faster than the other rotors. It is going to be specific for isopycnic separation, etc. So let's talk more about it. When I say vertical rotor, so vertical position which is parallel to the shaft. So there is no specific angle, right? So the rotor is fixed at a zero angle as compared to the central axis, right? So tubes are aligned vertically. So they are very parallel to the central shaft all the time. So during the acceleration, when centrifugation is started, the rotor starts moving, right? The solution in the tube is going to get reoriented. Now, how it gets reoriented, you see, it was horizontally spreaded. Now, what are the lines they are showing you? They are in vertical positions, right? So the particles they get reoriented at 90 degrees during the acceleration, and they lie perpendicular to the axis of rotation. Right? So these are the 2 points, and rotation and parallel to the applied centrifugal field. Just you have to remember and add to this point, that is when the vertical rotors they are accelerated, then the solution in the tube reorients to 90 degree, right, and lies perpendicular to the axis of rotation. So axis of rotation, if you talk, it is perpendicular to that. And if you talk about the applied centrifugal field, the orientation of the particles or sedimenting materials is parallel to the applied force. So perpendicular to axis and parallel to applied centrifugal field when you are running a vertical type of rotor. Now, the sedimenting particles, when you observe, uh, the uh, the particles are spreaded here throughout the diameter, right? Throughout the diameter of the tube. So they are spreaded throughout the diameter of the tube, and the vertical tube rotor, if you think about the path length. Now, what are the factors that you have to remember? Whether the how is the orientation of the particle? What is the angle of the tube with respect to the shaft? What is the angle of the particles when they start reorienting? So, when they start reorienting, they are perpendicular to shaft and they are parallel to centrifugal field that is applied. Third is how much distance the particle has to travel. Shorter the distance, better sedimentation, right? So when it is vertical type of rotor, the the particles have to travel shortest possible distance. So shortest path length for the particles is going to be one of the features when you are talking about vertical rotors, right? Now, when the shortest distance they have to travel, naturally sedimentation of particles can be achieved very fast, very quickly. So, and it is going to be quicker than swinging bucket rotor and fixed angle rotors, because R minimum, do you remember R minimum, R maximum, and R average we had discussed in yesterday's lecture. So, R minimum is greater, and due to the tubes being at rotor's edge, right? So, minimum is see this is the tube position in the fixed angle. So if this is a central shaft, so R minimum is very less distance. But as against that, if you talk about this vertical type of a rotor, now this is the shaft and this is the entire distance. So R minimum is equal to R maximum, right? In case of vertical rotors. So any distance you measure, whether R minimum or R maximum, it is going to be more, and it is more, or you can say greater, as compared to that in fixed angle and as compared to that in swinging bucket rotor. All right. So larger minimum centrifugal field is going to get generated. So distance, path length, and r, the distance, are the factors which decide the amount of centrifugal field generated. We have seen it in yesterday's discussion. So more the distance, more is going to be the centrifugal field generated, right? That is what we have talked. So R max will experience maximum centrifugal force. R minimum will experience minimum centrifugal force. But in case of vertical rotors, R minimum is equal to R maximum. So the particles or sedimenting materials are going to experience larger centrifugal field, right? So the pellet is going to be formed and is going to get deposited along the entire length of the outer wall, along the entire length of the outer wall of the centrifuge tube, and which is one of the disadvantages, you can say, because it will tend to fall back and it will get mixed up again. So this is one of the limitations. The speed separation is good, but particle sedimentation starts on the outer walls, so falling back of the particles into the running solution is also possible. So that is one of the disadvantages, or you can say limitations of vertical tube rotors. Now there is another one that we have to talk about is zonal rotors. Right. Now just now I mentioned about the wall effect. That is when the particles are migrating under applied centrifugal field, they move outwards, out to the outer wall of the tube, they slide down the tube and they settle. At the same time, convection currents are working and they are going to interfere. Similarly, when the particle hits the wall of the tube, it is going to be a kind of a what you can say, kind of an obstacle in the movement of the particle. So it is going to get pushed back from the wall to the center of the tube again, to small distance, of course, not uh, uh, randomly anywhere, but again it is coming back. So this is referred to as wall effect, and that needs to be minimized, otherwise separation is not going to be efficient. And there comes the role of zonal rotors. So zonal rotors, as you can see, is can be a batch type or continuous flow type, that is continuously operating, like industrial rotors, right? Or maybe a batch type rotor as you run in the department, or in the experiment in the lab, right? For separation of DNA, etc., etc., they are batch type, right? So but the zonal rotors can operate in both ways, batch wise or continuous flow type. Now when you are talking about the different types of batch type rotors of zonal type, they differ in the method in which they are loaded and unloaded. What is the difference between batch type and continuous type? That is important, because if it is batch type, it can be filled in one go and the pellet is recovered at the end. But if it is continuous, then inflow of the sample and separation of the uh, material, that is going on simultaneously. So the feeding method, the centrifuge is different. So there are, of course, low speed batch rotors, which are going to be, say, 5,000 revolutions per minute of zonal rotor types. And they are made up of aluminum, having thick, transparent top and bottom. So you can directly examine the particles which are sedimenting during the centrifugation process. Of course, you have high speed zonal rotors also, which are going to work at about 60,000 revolutions per minute. And when you are talking about any of these batch type rotors, these are generally large cylindrical containers or hollow bowls. So if you see the section of it, it is something like the entire circular area of the centrifuge inner body is divided into four quadrants, and each quadrant is going to act as a centrifuge tube, like us. The section itself is going to hold the sample. So it is not as in earlier case where you have multiple sockets and multiple tubes are placed. It is the circular area is divided into four quadrants, and each quadrant is going to work as a cell of the centrifuge. So another thing is, the center of the rotor has a core to which is attached the assembly, which is going to allow entry of the sample if it is going to be of continuous type, right? So you can have continuous type zonal rotor, or you can have batch type zonal rotor. The difference is, in continuous zonal rotor you are going to have uh, entry of the liquid sample continuously happening, and the outlet is going to allow the removal of the supernatant particles are going to get sedimented, right? So batch type, if you talk, they are about 300 centimeter cube to 2000 centimeter cube capacity, right? And of course, they can be used with gradient materials also. So gradient material is going to be filled in the entire enclosed space, and you can run it. So in short to say, and the zonal rotors are going to minimize the wall effect. So efficiency is good. They can work in batch mode or continuous flow type. They can be of high speed and low speed or average speed types rotors. In low speed batch rotors, it can be up to 5,000 revolutions per minute. High speed batch rotors, zonal type, can be working at 60,000 revolutions per minute. And the design is such that each rotor is like a large cylinder, and the interior of it is divided into hollow bowls. So each bowl is going to act as a centrifuge cell, and you can observe the actual centrifugation process that is running. Right now, let's look at how it is going to be when I say ki you are seeing the particles that are getting separated. Now, can you imagine the particles here? These are the four quadrants, right? Just see these margins, right? Separating walls. So, in the parallel to these separating walls are the sample inlet, or the sample is overlaid on the surface of the chamber or the cell at the entry point. So this is the center point. Here also you can have a entry point, or you can have an entry point which is parallel to this divided divisions or the walls, the septa, the that is dividing the entire thing into chambers. So this is the outer wall for this particular segment. This is outer wall for this particular segment. So entry point of the sample could be from the center. You are going to have pipelines, and once you are going to uh, 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 load the sample here, it is going to run and move outwards, right? And the larger particles are going to settle on the outer boundary. Smaller particles are going to be on the inner boundary. Of course, you can use gradient also. So this chamber is filled with the gradient, density gradient, like cesium chloride or sucrose gradient, and from here you are loading at the top of it. You are loading the sample, and centrifuge is allowed to run. So what will happen on the outer side of the cabin? You are going to have larger particles sedimenting, and near the center you are going to have smaller particles which are going to get sedimented. So this is about the zonal rotor. What is the importance of zonal rotor? To minimize the wall effect. Falling back due to convection currents is not going to happen here. Okay, now another type is here, that is elliptical type of rotors. As you are seeing here, uh, again here there are four chambers as you see, and each chamber is going to, if you take the cross section of that, it would look like this, right? So here is your sample inlet, and uh, when the centrifuge is accelerated, you can observe the difference in the three stages, right? So what you are observing here is, right? So what you are observing here is the direction of centrifugal force, right? So this is towards this arrow. Can you see this? Now, then low centrifugal force at this end, high centrifugal force at the narrow end. At the wider end, you have low centrifugal force, and at the narrow end, you have high centrifugal force. So this is towards the shaft, central shaft, and this is away from the shaft. So away from the shaft, you are going to have high centrifugal force. So uh, separation of the particles would be uh, would be occurring in this particular manner, right? When it is working, it will spread out. See, the particles are uniform here, they are settling, and major is going to get settled at the outer tip. So elucidator rotors are working in this particular fashion. The schematic representation itself tells you how the elucidator rotors are going to work. These are again the conical chambers. Now this is a schematic diagram which shows the comparison. What is the comparison? The comparison is of how different types of rotors are going to work, and how reorientation of sample is going to happen, and how uh, reorientation of the particles when the centrifuge is accelerated and deaccelerated, and how it is going to achieve the pelleting. So this is the case when you are having fixed angle rotor. This is the schematic diagram that represents fixed angle rotor. Here is the sample. As you hold it in the position, it is little tilted, yes, because the tube is at 14 to 40 degrees with respect to central shaft. So orientation of the sample can is indicated with these lines. So can you compare the orientation of these particles which is indicated by lines? So see the lines, the direction of lines in the first, that is fixed angle rotors. See the direction of lines which represents uh, reorientation of the particle in the vertical tube rotor, right? They are parallel. They are parallel to centrifugal field, but they are perpendicular to central shaft, right? Now second, and this is the third, is swinging bucket. This is the way it is going to get reoriented, because the tube is going to flank out, get placed horizontally, and the particles which are sedimenting will get reoriented in this manner, right? So this is a comparative account of three different designs of rotors, right? So when I say the types of rotors, um, the selection of a particular rotor is important depending upon what is the purpose for which you are using it, right? So uh, uh, in the rotor, when you are talking about the reorientation of the particles is very important, and it is changing in each type of rotor. So this is about the rotor designs, and now this is about the rotor care. So it is very simple, that you have to rinse it properly. It is carbon fiber, aluminum or titanium rotor materials, right? So you should not use any corrosive materials like acids or ethanol to clean it, right? But you need to disinfect it, right? Because you are centrifuging different types of cell suspensions, etc. So to avoid um, infection or contamination of the material, you have to disinfect these. Of course, certain times you can go for sterilizing it. So rotors can be sterilized using autoclaving or UV exposure to kill the infectious agents. And of course, in rotor care, one more thing is that you should assure that rotor is properly fixed in the centrifuge. Now, last but not the least, we have to talk about one factor, that is factor K, right? So when I say K factor, here it is a common parameter which is going to describe the efficiency of centrifuge rotor system, and that is going to be helpful when you calculate K value. It will be helpful to choose which rotor shall I go for, right? So different types of rotors and selection of rotors. So the greater the minimum radius, greater is the centrifugal force that we have seen. R minimum is going to have greater centrifugal force at the top of the tube, and faster separation will proceed. In addition, the centrifugal force at the R minimum defines a particle's minimum size for starting sedimentation. So these things we have talked about, right? So the shorter the path length, that generally arises from a more sharply angled tube. So fixed angle rotors will have shorter path length, we have seen. So K factor is a simple measure of overall rotor efficiency. That is what I have said. Now, how can you calculate it? See the formula. K is equal to 2.533 into 10 raised to 5 into log of R max upon R minimum, and this entire system is divided by RPM upon 1000 whole square. Now This is one way of calculating it. There is another formula which is the rearrangement actually, which is K is equal to ln R max upon R minimum upon n square into 2.533 into 10 raised to 11. Now what is n here? N is the maximum rotational speed, right? Maximum RPM that you are going to rotate it. K is the K factor of comparative centrifuge. How to choose a centrifuge? That is going to depend on K factor. R max, that is the radius at maximum, R minimum, that is the radius at minimum, and sedimentation distance is R max minus R minimum. So if you put these values, you can calculate the K factor, and K factor can be utilized to calculate the time of sedimentation. So this is the formula for that. We will continue with these formulas in the next lecture.